When wind flows through a wind farm, every turbine takes energy out of the wind, slowing it down for the turbines behind. This creates a phenomenon called a wake behind the turbine. These wakes are like a tube of reduced wind, which over time is being filled up by mixing it with the surrounding wind. A single turbine will always try to extract the maximum power from the wind. Wind farm control is the process of controlling the individual turbines in a wind farm in a collaborative fashion, getting a higher yield from the available wind resource and reducing the loads on the individual turbines. There are essentially two possibilities to do this. The first one is called induction control, where you down-regulate the front turbine and leave more wind for the following ones. The other way to do it is to steer the wake away from the turbine behind. The intentional yawing of the turbine turns the wake so that it does not hit the downstream turbine at all, thereby allowing the second turbine in the row to run in clear air. The same controls can be used to reduce the loads on the turbine inside the wind farm. To provide services to the grid, for instance faster frequency control, advanced control approaches such as virtual synchronous machines are used. Therefore, wind farm control is quite a complex and multi-dimensional riddle to solve. But an improved wind farm controller could in principle both increase the production and prolong the lifetime of the turbines, just for the price of a software upgrade. In order to address this, the European Commission is funding TotalControl, a Horizon 2020 4-year research project. 8 partners from 5 countries are working together in a collaboration from academia, manufacturers, and wind farm operators. A large part of the project will be computer modeling of the controllers in a wind farm of various levels of sophistication. At the high end, large eddy simulations requiring thousands of core hours on a supercomputer verify the controllers that are devised. But for controller development, some faster but lower fidelity models are needed. These quicker models allow us to run thousands of simulations with different parameters of the wind farm controllers and thereby to develop the control strategies. The faster models can also be used in the control approach itself, going from pre-computed open-loop control to closed-loop control, where a model of the wind field in the wind farm is updated every second to aid the controller. To verify the findings, we will do a measurement campaign at Vattenfall's Lillegon offshore wind farm between Copenhagen and Malmö. The farm is already equipped with load sensors and records power and many other turbine data every second. We will add a wind scanner, a synchronized laser-based system capable of measuring the wind speed and direction at any given point in the air. Using this, we can determine the effect of the controller on a live wind farm. To work really well together, the individual turbines need to play along. Currently, their individual turbine controllers are set up to optimize the wind flow for themselves and not for collaborative behavior. The wind farm control friendly turbine controller will be implemented at ORE Catapult's 7 megawatt turbine at Leavenmouth. Again, for the wind flow, we employ a LiDAR system, capturing the wind flow in front and behind the turbine. From the difference, we can establish the effect of the turbine controller. We can also assess the additional loading of the turbine in yawed conditions. Ultimately, the aim is to develop a virtual research laboratory for wind farm controller development and multi-fidelity validation. The final outcome will be an open-source TotalControl toolbox, which will be made available to the wind energy community.